Hi everyone, it's Miss H, and today we're going to be looking at our second in our unit on work, power, and simple machines, and that is power. Okay, so what is power? Power is the rate at which work is done, or another way of saying that is how quickly work is done. The unit used to measure power is the watt. A watt is equivalent to 1 joule per second. A watt is a very small unit. It's what you think of when you think of your light bulbs, right? There are 60-watt light bulbs, 15-watt light bulbs, that sort of thing. It's a relatively small unit. So a lot of times when you're talking about like the energy for a whole house or for a power plant, that kind of thing, you're usually going to be talking about kilowatts, which is 1,000 watts. We'll also sometimes express power as horsepower. That's typically what we think of when we're talking about like car motors, that sort of thing. And that's really because it was the equivalent of how many horses were needed to do that amount of work, and so that's why the horsepower came about. 1 horsepower is the equivalent of about 746 watts, so a horsepower is significantly larger than a watt is. It's not something we're likely to use very often in this class, but it is a possibility of something that you would see, so that's why I want to make sure that you know that conversion. It should be provided for you on any kind of test that you would be given a question about that on, because every time we're going to use the formula, we're going to be using it in watts, not horsepower. In fact, it needs to be in watts in order to make the formula work. So what is the formula for power? The formula for power is work over time. Anytime you see the unit, or anytime you see that something is the rate of doing something, it's going to be over time. So if we put this into our triangle, work goes in the top, power and time go in the bottom. Remember, anytime you have something in a numerator position, it has to go in the numerator in that triangle. It has to stay in the top of the triangle. Okay, so notice that watts is also a capital W like power or like work is, so it's very important that you keep your 2 capital W's separated. So if the W is attached to a number, that means that it is the unit watt. If the W is by itself in a formula, that is representing work. So keep those capital W's straight. Okay, it's a little bit tricky, but you have to make sure that you keep those 2 capital W's straight. Let's take a look at some example problems. How much power is needed for a motor to do 3,000 joules of work in 1 minute? So let's start with our identifying. So 3,000 joules, that's our work. 1 minute, that's our time, and we're asked to solve for power. So we could say joules divided by minutes, but that's not going to work. We have to have our time be in seconds in order to make this formula work. So we do have to convert our 1 minute, and we should know that 1 minute is 60 seconds. So I'm not going to bother to show that conversion. I'm just going to go ahead and say 60 seconds instead. So power equals work over time. That step 2 is writing the formula. Step 3, we're going to plug in our numbers. So 3,000 joules over 60 seconds. And when we type that into the calculator, we get an answer of 50 watts. 50 watts of power are required for a motor to do 3,000 joules of work in 1 minute. Question number 2. How much work is done by a 2,000 watt motor in 30 seconds? Sorry, 200 watt motor in 30 seconds. 200 watt motor in 30 seconds. How much work is done by a 200 watt motor in 30 seconds? So let's identify 200 watts, that's power. 30 seconds is time, and we're asked to solve for work. So if we look at our triangle, work, power, time, solving for work. So work equals power times time. Notice that whether you're using the work formula or the power formula, you're going to be multiplying when you're solving for power. So that does make, solving for work. So that does make things a little bit easier. Anytime you solve for work, you're always going to be multiplying. So now step 3, I'm going to plug in my numbers. So 200 watts times 30 seconds. So that gives me a work of 600 joules. 600 joules of work are done by a 200 watt motor in 30 seconds. Example number 3. A student does 6,000 joules of work to charge up a 60 watt incandescent light bulb. How long will the bulb stay lit? So step 1, 6,000 joules, that's my work. 60 watts, that's my power. How long will the bulb stay lit means I'm solving for time. So if I put this into my triangle, solving for time gives me work over power. That was step 2, the formula. Step 3, let's plug in our numbers. 6,000 joules over 60 watts. And so that gives us a time of 100 seconds. 100 seconds that light bulb will stay lit. Example number 4, how much longer would a 15-watt compact fluorescent light bulb stay lit? So we're going to look at the same question we did before, that students doing that same 6,000 joules of work, but now they have a 15-watt incandescent light bulb instead of a 15-watt compact fluorescent light bulb instead of a 60-watt incandescent light bulb. So we're still going to have that 6,000 joules of work from the previous problem. Okay, but now our power is going to be 15 watts, and we want to know how much longer. So again, we're going to be solving for time, but we're not just going to straight solve for time. So time, as we just said, was work divided by power. So that's going to be 6,000 joules of work from the previous problem divided by 15 watts. That gives me 400 seconds. That's not the answer, though. That's how long this bulb would stay lit. It wants to know how much longer this bulb stays lit than the other one. So I have to take that 400 seconds minus the 100 seconds from the previous problem to give me 300 seconds longer. So it stays lit for 300 seconds longer than the 60-watt light bulb does. And that's really a big part of why there's a push toward moving toward compact fluorescent light bulbs and even LED light bulbs, which are even more efficient, because it helps to, the bulbs will run longer for the same amount of work being done. Okay, let's take a look at one more example that's a lot more complicated than the other ones. How long will it take a 100-watt motor to lift a 20-kilogram object a distance of 2 meters? So this question is more complicated because it takes more than one formula to solve it. But other than that, it really is just a straightforward problem once you know which formulas you need to use. So let's start with our identification. 100 watts is our power, 20 kilograms is a mass, and 2 meters is a distance. It wants to know how long, so we're solving for time. In order to solve for time, we just did that in the previous problem. That's going to be work over power. But I don't have work. So in order to solve for work, I have to do force times distance. But I don't have a force, so in order to solve for force, which is going to be the weight of the object is mass times acceleration. So I'm going to substitute in for each of these things. Okay. And so what I'm going to end up doing is I can do this as either 3 separate problems, or I can take and I can substitute m times a in for F, and I can substitute F times D in for W in the other problem. So that's actually what I'm going to do. So time is equal to M times A times D over P, because I need to do MA to get for F, D to get for, and then FD to get for W. So that's going to be 20 kilograms times 9.8 meters per second, because that's acceleration due to gravity squared, times my distance of 2 meters, all over 100 watts. So T equals, that's going to give me 392 joules over 100 watts. And so that's going to give me a time of 3.92 seconds. There's a decimal point there. So 3.92 seconds. So again, it's a more complicated problem, but once you actually know what to plug in where, it gets really straightforward. Okay, that's pretty much everything for power.